Good morning, everyone, and welcome to today's webinar. Today's webinar is Expert Panel on Heat Pumps, the Future of Industrial Heating, presented by Phil Johnston and Clay Monahan. We appreciate you all joining us today as we learn about the fundamentals, performance metrics, and practical applications of industrial heat pumps and how they're driving decarbonization. I'm Chase Bean, Vice President of Engineering and Revenue at Steam Management, and I'll be your host for today's webinar. I'll be moderating the session and your questions for our experts, so I encourage you to submit those in the chat throughout the presentation. We will also have a few polls throughout the presentation, so be sure to participate when you see those pop up. Additionally, for those looking to earn PDH certificates, please email me at cbean@steammgt.com to request your certificate after the completion of the webinar. For more details, along with access to past webinars, go to steammgt.com/webinars. At Steam Management, we specialize in optimizing steam and utility systems, starting with system assessments and energy audits to identify and develop projects for efficiency improvement, all the way through turnkey implementation. Our services range from traditional maintenance and equipment retrofits to customized engineered solutions and capital equipment replacements. We are committed to delivering projects that reduce costs, enhance reliability and safety, and lower carbon footprint. Our teams work with federal, public, commercial, and industrial facilities across the U.S., helping to achieve long-term budget efficiency and sustainability goals. And now to introduce our guest speakers. Today's session brings together two engineers with deep experience in industrial energy efficiency and decarbonization. First, we will have Clay Monahan, Head of Solutions at Atlas 602. Clay is a chemical engineer with over a decade of experience in industrial energy reduction. He started his career in the oil and gas sector and has since worked as an energy efficiency consultant, helped shape utility incentive programs, and most recently led the engineering team at a thermal energy company. Clay's worked across a wide range of industries, including oil and gas, chemicals, food and beverage, metal, pulp and paper, mining, and more. Joining him is Phil Johnston, Director of E4E Solutions. Phil is a seasoned consulting engineer with over 10 years of experience in industrial decarbonization. He's engineered and managed hundreds of energy projects across various sectors from concept through construction, and his focus is always on tying capital projects to meaningful business outcomes. We're thrilled to have both of them here to share their knowledge and experience. E4E Solutions specializes in the development, design, engineering, implementation, and financing of innovative solutions that deliver energy savings, reduce operating costs, and modernize and renew utility system infrastructure. They have a successful track record of developing high ROI, sustainable, cost-saving projects for industrial, manufacturing, and commercial clients around the world. Atlas 602 specializes in assisting large industrial manufacturers with reducing carbon emissions. The company collaborates closely with clients to develop tailored decarbonization roadmaps that align with their specific goals and return on investment targets. By emphasizing a hands-on, in-depth approach, Atlas 602 ensures that proposed solutions integrate seamlessly into existing operations without disrupting throughput, safety, or quality. Now, on to the presentation. Our learning objectives today are basics of heat pumps, defining performance, heat pump viability, identifying heat sinks and heat sources, pinch analysis, heat pump applications, and project examples. So with that, I'll turn it over to Clay, and I think we're starting with a poll right here. Yeah, so just participate in that poll there and hit submit, and it should close out of your view. And take it away, Clay. Thanks.
All righty, thanks, Chase. Okay, so excited about what we have for you today. Basically, we're going to start off with myself going through the basics of heat pumps and the principles and sort of what makes them, more efficient, more viable. And then Phil's going to take us through some real world examples and how that might look in a plant. So it's going to be great. Let's dive in on the basics of heat pumps. So we're going to just start with the basics. So heat pumps source heat and then upgrade that heat to a useful output temperature. Heat pumps use a refrigeration cycle to accomplish this. This can be open cycle, but typically it's a closed cycle. So heat pumps look a lot like a chiller. So let's do a quick review of the refrigeration cycle before we start getting into the theory. So the evaporator is going to evaporate refrigerant as it picks up heat from some heat source. That refrigerant in the vapor phase goes to a compressor. That compressor compresses that vapor up to high pressure conditions, high temperature conditions where using electricity. And then that refrigerant flows to a condenser where, as the name suggests, the refrigerant condenses at that high temperature that's going to be higher than wherever it's rejecting its heat to the heat sink. After that, we have liquid refrigerant that moves through an expansion valve back to the evaporator to start the process over again. Okay, so starting with the basics. So heat pumps have two energy inputs, the heat source and the electricity driving the compressor. I think sometimes the thing that's difficult to wrap your head around with heat pumps is, you only put a little bit of energy in and you get a lot of energy out. The key is the energy you're putting in from the form of electricity, you also have to account for the heat that's coming in from that heat source. You're not creating energy. It's just that there's two things on the side, on the scale of the inputs compared to the output. The output to the heatsink is the sum of those two inputs. So the heat source plus the electricity kW equals the heatsink kW. So just real quick, putting that into practice, just give you a second to think about this before I click the next animation here. But if we have 300 kW of heat, just a power rate of the heat that's coming into the system, just like the electricity here, what I have is 100 kW, what would that output energy be, assuming no losses, perfect system here. Just a second to think about it to yourself. 400 kW. So it's just the 300 plus the 100 equals 400. So when you see the 100 kW going into the heat pump and you see 400 coming out, that means you have 300 worth of energy input or power input coming from this heat source. Okay, so heat pump performance is measured with a metric called coefficient of performance, or COP. COP is the ratio of the benefit provided by the heat pump divided by that input electricity. So the good stuff divided by the stuff you got to pay for. So COP is equal to that heat sink kW divided by the electricity kW. So if we go back to that example, we have 100 kW benefit. We're providing 100 or 400 kW of heat at a cost of 100 kW into the system. So that COP, give you a second to think about it to yourself for a second before I click next. That COP is going to be 4. It's just that 400 divided by 100. So that's the basic principle of COP. And now we're going to get into defining the performance with a few critical parameters. So HEOP, or heat pump COP, is a function of two basic principles. First is the theoretical COP. What's the maximum possible COP we can achieve? And that's just going to be defined by the temperature conditions that the heat pump is seeing. So that maximum theoretical COP is just going to be that hot temperature that we're trying to achieve divided by the lift, or that temperature delta across the heat pump, the hot temperature minus the cold temperature. So the second principle of that thermodynamic is the thermodynamic efficiency of the heat pump. So that theoretical, T hot divided by the temperature delta, we're never going to achieve that perfect thermodynamic condition just from losses in the system. So depending on the heat pump technology, we're going to achieve some percentage of that ideal percentage, or of that ideal COP. So this thermodynamic efficiency is usually defined as the percentage of the maximum possible efficiency, or that Carnot efficiency. And that efficiency is, the COP actual divided by the COP Carnot, or that you can think of that as just maximum COP achievable.
Okay, so that actual is like your actual power input compared to your actual thermal output, including parasitic losses, any other efficiencies in the system, right?
Yeah, we'll get into some math examples here, but it's basically what's your actual COP that you can achieve versus what's the theoretical maximum. Because you can do the math on what the theoretical maximum could be, but you're never going to achieve that. You're only going to achieve some percentage of that. So for this system, just theoretically, our base COP case, let's start there. We have an 80 degree F heat source and 160 degree F heat sink. So let's do the quick theoretical calculation. That theoretical maximum, the COP Carnot, is the temperature hot divided by the temperature delta. You do have to convert to absolute temperature units, whether that be Kelvin or Rankine. And for any European colleagues on here, apologies for doing this in Rankine, but if we have 620 divided by the temperature delta of 620 minus 540, that's going to yield us a COP of 7.8. Before we move on to seeing the effect of that theoretical or the actual versus the theoretical maximum, let's just go into a few examples to see how temperature influences this maximum COP. So going back to our slide, if instead of 160 degree heat sink, we have 180 degree heat sink, so we have a higher lift across our heat pump. Now we're up to 100 degrees Fahrenheit instead of that 80 degree mark. Let's figure out our new COP. Same thing, using our formula and converting to the absolute temperatures, but now having that higher lift, we see a drop in the COP to 6.4. So higher lift across the heat pump is going to lower our COP. Let's do one more example, but instead of increasing the heat sink temperature, let's increase the heat source temperature up by 20 degrees. So now we're back to that 80 degree lift, but we have a higher quality heat source. Again, same formula, same conversion. Now we're seeing a COP of 8. So the takeaway there is higher heat source temperature is going to equal higher COP. And that's really the two effects that you want to keep in mind. The higher the heat that you're sourcing, the better the COP is going to be, and the higher you have to go, or the temperature lift that heat pump has to achieve, the lower the COP is going to be. Okay, so let's start applying some of those theoretical or actual efficiencies to that theoretical efficiency. So this number can vary significantly, but is a rule of thumb for a packaged solution. 50% is a fine estimate. It can be lower than that, it can be anywhere in the 40 to 60 degree neighborhood. And I'll also say that for an open cycle system where we can get into those sorts of questions if folks want. This is things like MVC/MVR. These can achieve higher efficiencies due to some advantages of working directly on the fluid that's going into the compressor. But 50% is a fine estimate for most applications. That's going to get you in the ballpark at least. So just going through those three examples we just went through, the 7.8, if we multiply that by 50%, we get 3.9, 3.2, and 4.0. So these are more typical COPs that we would see, from actual products and actual applications. Okay, so I'm going to go into some heat pump viability real quick. Any questions before I dive into that?
I'm not seeing any in the chat yet, so.
Okay. All right, so we have theoretical COP, and we have that in mind, but what does that mean, and how does that actually affect project viability? So comparing heat pump performance against existing fuel-fired systems is really the metric that we're looking to beat out as those existing fuel-fired systems. So steam system efficiency can vary widely, and a lot of attendees of these webinars, and Chase, I know you all can speak intelligently to this, but steam system efficiency can swing all over the place. A boiler efficiency, typically the rule of thumb is 83% efficiency, but between heat losses and leaks, the system efficiency of where that heat's actually delivered to an end user can be more like 70% or even lower. Chase, I'm sure there's been lots of topics on various webinars on this, but if we say 70%, you can use 65. I've seen that number out there, but 70% is a conservative number for a quick comparison between these systems.
Yeah, definitely. Clay, let me interrupt you for a second.
Please do.
There are a few questions in the chat. So one is there a definition of what makes a heat pump an industrial heat pump? What would you say there?
Yeah, so that's a good question. I would say, industrial heat pumps more a matter of the product you're selecting from. I think there's some that blur the lines, especially on the hot water application side. If they could go into a commercial building or they could go into an industrial facility, but there are dedicated industrial heat pumps or systems that use refrigerants like ammonia or some of those open cycle systems like the MVR and the MVC. You're not going to see those in a commercial application. So there are specific heat pumps that are geared towards those industrial customers. But if it's a CO2 heat pump or more traditional refrigerant like HFO heat pump, those could be seen in either application, I'd say.
Yeah, like ones that are kind of geared towards process heating, right? Or industrial heat capture, right? Okay, the next one is what kind of applications have a 100-degree F heat source? And I do think that we talk about that later in the presentation, so we can hold off on that one, unless you want to add something there.
Yeah, yeah,
Yeah, go ahead.
yeah. Phil's got good stuff lined up, but in the industrial setting, well, I guess, just starting on the more, utility-based systems, if there's things like, chillers or, if you have an ammonia refrigeration system, you're not going to see temperatures that high, or at least certainly not average temperatures that high. So you'd have to go things to like hot exhaust sources from a dryer, or if that works with, existing boiler operations or a CHP unit, those exhaust sources are going to have, significantly higher, not just dry bulb temperatures, but wet bulb temperatures, which really drives the heat available calculation.
Okay.
And like you say, Chase, we're going to get more into that later.
Right. Somebody asked what was the 50% estimate in the previous slide? Is that a system-wide efficiency?
Yeah. So if we look at, refrigerant based heat pump, and you're lifting from that 110 to 160 degrees, uh, it's going to have oil cooling the system, and that oil needs to be cooled. That's one example of losses. It's going to have various points in the system where it's losing thermodynamic efficiency. So if you do the temperature calculation and the theoreticals, 8 as a COP, let's say, you're only going to be able to achieve 4 from that because of the heat you have to reject from losses in the system. So, that's
Yeah.
through the drivetrain, that's mechanical. Yeah.
Yeah, pump efficiency, casing losses, like heat thermal losses, yeah, all that. Okay, one more. Aren't we generally using heat pumps for heat recovery? Yes, that is the concept of them, and they're going to talk about that later as far as where those heat recovery sources come from. So I think let's move on and hopefully we'll address that later on.
Great. Okay. Yeah, Phil definitely speaks directly to that. Okay, so just switching back here to the heat pump viability, just establishing some base cases here. So hot water systems, these can have much higher efficiencies than a steam system. 90% is close enough, but even some of these, direct contact units, they can have really high efficiencies. You're still going to have, losses from, through insulation and all that as you distribute the hot water, but uh, these these systems are going to have, higher efficiency than their steam counterparts. But typically, when for most of the folks on this call, the relevant base case is going to be that steam system. Okay, so let's go through some different examples here just to see how the energy prices and the heat source temperatures affect system viability. So if we have an average heating demand of 3 MMBTU per hour to generate 160 degree F of hot water, let's look at the annual energy input required for each system. 3 MMBTU per hour, that's a fairly significant load. For some folks on this call, it might not be that big. For others, it might be pretty sizable. But this might look like something like a CIP system, especially at that 160 degree mark. This could roughly look like that for a food processing plant or just domestic hot water. This fits within those parameters, just to kind of put it in terms of what your facility might look like. So a steam boiler with an efficiency of that combined system efficiency of 70%, the annual energy to meet that demand at the end user would be something like 37,500 MMBTU. A hot water boiler might be able to do it at 29,200 MMBTU, and a heat pump at a 3.9 COP using that same calculation with the 50% actual achievable COP efficiency factor applied is going to yield 6,800 MMBTU, which is just an energy unit, just like kWh. So if we convert to kWh, it's about 2 million kWh. All right, so we have our different energy inputs, and just pausing a beat on this. If there's any questions on translating from one to the other, happy to field them. But it's just they're both energy units, and you can convert from one to the other. Cool. All right, so what's the annual cost of these systems if we're at $5 an MMBTU and 7 cents a kWh? I'll go through a different few cost scenarios, but $5 an MMBTU is probably a fair enough estimate. I looked up Henry Hub pricing this morning, and for the last 3 months, it's been right at $4.10. So with distribution charges applied, and you got to pay the local utility, it's going to get up towards $5. 7 cents a kWh. This is closer to an industrial rate. Could certainly be more or less than that. We'll get into that in a second. So a steam boiler under these parameters is going to cost 188,000 with that same energy value we just calculated. Hot water 146, and then a heat pump is at 140. So in these conditions, we're only seeing about $48,000 a year saved. And I think it's worth noting, these systems at $3 an MMBTU to get the heat pump purchased and integrated. We're looking on the scale of at least $1 million to get this in. So, $48,000 a year saved isn't necessarily something that's going to be viable. So let's look at, levers we can pull to improve the economics of this project or theoretical scenario. So same pricing, but what if we have a 110-degree heat source instead of 80 degrees? Same as above for the first two above, and then $87,000 annual operating cost for that electricity that we have to purchase for this heat source. So we've doubled our savings, or actually over doubled our savings, just by going out and getting 30 degrees extra of heat. I say just, for somebody at a hospital, for example, getting 110-degree heat isn't necessarily, as easy when you have to switch from, the cooling towers over to something like boiler exhaust or CHP exhaust, but those heat sources are still there. And Phil, we'll get into that of where you can look besides just your chillers. All right, so let's keep the heat pump metrics the same on the temperature side, but change the energy pricing. So if we have $4 an MMBTU and 5 cents a kWh, so if you're down in Texas or something like that, where you're going to be closer to, or you're not natural gas distribution constrained, like we'll see on the next slide, and your electricity, you have the ability to go out and get an energy supplier that could do some hedging and some stuff to actually bring down your electricity cost down into this 5.5, maybe even 6 cent realm. But let's use 5 as the example, just as a sort of a conservative case. Their steam boiler cost goes to $150,000, 117, and then $62,000 on the heat pump. So that's going to be $88,000 a year saved. Obviously, if your utilities just cost less, your savings are going to be less. And then if we're out somewhere like the Northeast, where we have more expensive gas and more expensive electricity, the steam boiler is going to cost significantly more. The heat pump's going to cost more, but the delta is going to be increased to 115,000. So Phil's going to get into spark spread, and that's basically the introduction to this concept and how that affects it. But your energy prices obviously have a big effect on the viability of the project.
Hey, Clay, I got some comments here before we get to your bottom line. Gordon Judd says the benefit of heat pumps can either be taking away from a process or adding heat to a process. In the best cases, heat pumps are located so they can provide useful energy simultaneously to both sides of the equation when heating and cooling. I think that's a good point, but I think in industrial applications, we're mostly seeing heating requirements that we're trying to meet. Would you agree with that?
No, it's a great point, Chase. I'll give an example of a food plant that I was looking at, last year, and they had a process where they were actually using just radiant coolers to cool off product before it went off to packaging. When actually with the radiant coolers and then a chiller. So by swapping the radiant coolers with a heat exchanger that would allow us to direct that heat to a heat pump, you could take some load off of the existing chillers. So you're gaining benefits on the chilled water side, and you're also creating, hot water or steam on the other side. So you're offsetting the natural gas consumption. So what we're talking about here in terms of these COPs are all the COP of the heating benefit. But this COP equation works just as well if you bring in other realized benefits, like on the chilled water side. So if you're offsetting, 1 MMBTU per hour of cooling demand, then you can add that to the benefit side, and your COP starts to go up because you're offsetting load off of systems that would otherwise have had to meet that demand. So no, it's a great point, and there certainly are industrial applications where that can happen. But yeah, these slides just focus on that heating benefit COP.
Okay, yeah, well said. That's interesting. That changes the whole equation. And I guess speaking of
Certainly.
factors of the equation, some people are commenting on their utility rates of 20 cents per kilowatt hour in Massachusetts. Someone else says 35 central Massachusetts. Yeah, and now somebody says the team at Central or Clean Power Research has built a remote residential block load calculator. Okay, that's interesting. You can check that out if you want. Anyway, okay, take it away, Clay.
Yeah.
Thanks.
Yeah, the Massachusetts folks, yeah, that's interesting. I mean, interesting's a interesting word choice. 35 cents and 20 cents. Yeah, I mean, I was trying to, get something that's at least in the realm of, what you all might be seeing. But the other benefit of being out in Massachusetts are more aggressive electrification incentives. We were just working on a project for a mining company where I think we're going to end up at something like 70% incentives available for this project. And that's going to be over $1 million in incentives from the state. So if that electricity price is narrowing the actual savings that you're yielding, at least, up there you have some additional levers to pull in the form of incentives. And then, yeah, you mentioned tools, Chase, so I wanted to mention that too. If you look at Renewable Thermal Collaborative, they have nice tools available to do, I think it's the initial assessment, and then there's a feasibility tool, and then they have a suppliers list on there as well. And then there's a Industrial Heat Pump Alliance that's sort of a joint effort between ACEEE and NEMA, and they have a heat pump evaluation tool as well. So there are certainly tools out there to help you calculate what these industrial heat pumps, might actually yield in terms of benefit, or at least get a first look anyway.
Okay, great. Yeah, we'll have to
Cool.
check those out.
All right. Oh yeah, we're doing fine on time here. Okay, so this will be our last slide, and then we'll get into a poll here. I just want to reiterate, heat pump viability is dependent on, that ratio of the gas and electricity prices. Like I said, Phil's going to get into that a little bit deeper here next. And then the heat source and heat sink conditions. The higher the temperature we can get, the lower the lift, the better. So use favorable rates, avoiding demand charges can change that effective electricity price significantly. And then using high quality heat and directly heat the end user where possible to avoid losses in a steam system, say, and heat exchangers, that's all good. So those are some high level thoughts. Anything on the theory side? Happy to field a few more questions before Phil gets into some, more real world applications of these theories. Cool. Well, Chase, do we want to do the poll then real quick?
I think it launched actually.
Oh, great.
Yeah, so this is I think this is like a word cloud thing. So you just type it in and it'll generate a word cloud as a result. Yeah, I think the number one response so far is cost. I got energy savings, cost and efficiency, initial cost, cycle cost, cost of operation. Yeah, interesting responses. Kind of what you would expect though. And now Phil's gonna take over and talk about applications in industrial settings, among other things.
Thank you, Chase. So Clay's done a really good overview of the basic theory around heat pumps and how they work. I'm going to get more into their applications and how they can be used in an industrial setting. So the first thing you have to do when looking at this is really understanding what the sources are and sinks are at your facility. I've thrown up some examples here. This is an exhaustive list for sure, but these are some examples of heat sources and heat sinks. Uh, in general, from the source side, it's a lot of waste heat. Whether you have a process that has some form of gas firing or heating that has an exhaust stack to it, that's certainly a good source of heat. You also have standard industrial equipment like boilers and air compressors that give off heat as well. So those are things to find on the source side. On the sink side, it's heating applications in the process or uh, inflows to a utility that have a heating component to them. Boiler feed water is a very common place to use this. Also, CIP or clean in place, if you're not familiar with the acronym, that's all the cleaning water, especially uh, in food and beverage and other, uh, you know, industries like that. Cleaning is a huge part of the heating load for the plant. So that's a really big heat sink.
So my impression, Phil, is that, and kind of also agrees with your list there, is that in most applications you're really needing a high temperature heat source. So like air source, ground source, heat sinks are kind of, there's too much lift there to at least when you're talking about generating steam or high temperature water. Is that fair to say?
Yeah, I mean the temperatures can vary. The golden goose is a low temperature heat sink because then you can throw pretty much anything at it from a heat recovery standpoint.
Hmm.
But those are fewer and far between in an industrial setting. So yeah, all this is really driven by temperature, and that really leads into my next slide, which is the pinch analysis. So if you're not familiar with this, what this is you've got the red line there, which is the hot curve. So that's your heat sources, and your blue line is the cold curve or your heat sinks. So what we're trying to look at here is there enough heat available at the temperatures we need it to serve all the sinks uh, that we have. And pinch analysis allows you to do that. Where those curves approach and almost touch each other, that is the pinch of the whole analysis and really drives how much you can do. So that's the delta in temperature that would be across a heat exchanger, and this drives how much heat recovery you can actually do. If the temperatures of your heat sources is too low, then this red curve would dip below the cold curve and you wouldn't be able to recover as much heat. Or if, looking at it from the other way, if your sinks require a really high temperature and you just don't really have a lot of high temperature sources, that blue curve would glide above the red curve and limit the amount of heat you can recover. So this is a really valuable tool when you evaluate heat recovery, applications. Going back to what Clay said about lift, that's a very important part of this. It what drives the electrical consumption of the compressor or the heat pump and drives the performance and efficiency. So when you're thinking about work uh, put into the system from an energy standpoint, it's really that compressor and it's lifting it from that um, low temperature in the evaporator to the high temperature in the condenser. This is really driven by pressure. So, that compressor is taking that low temperature, low pressure gas and pressurizing it and heating it up at the same time to that high temperature, high pressure gas that goes through the condenser. This is a picture of a real live heat pump at a dairy factory that we did work with in the last year. You see some of the major components. Usually that screw compressor and motor sit on the top of the package there. And this one actually has a remote evaporator. So the evaporator is not on the skid here, but you always have a control panel there with a screen to look at, all the different inputs and outputs. And we'll get more into that on the next slide. So when, looking at a heat pump, Clay already went over this, but really what's driving performance there is the work that the compressor is doing and the heat that's being rejected. That's how you evaluate the performance. So in this real life scenario, we have a few points here that we can see to see how this heat pump is performing. You have the suction pressure and discharge pressure across that screw compressor. So that's the pressure that's being added by the screw compressor. Once that high pressure vapor, which is superheated, which is just a fancy way of saying it's much hotter than a saturated condition, or you know basically has more heat in it than normal. That goes through the condenser and rejects all the heat. So we go from 200 degrees before the condenser to 100 degrees. So that's quite a bit of heat we're rejecting through the condenser. In this real life scenario, we can also look at the COP, and you can see that the work in real time from the motor, which is driving the compressor and pressurizing that gas, is around 350 kW, and the heat rejection is significantly higher than that. It's around 1500 kW. So that roughly comes out to 4 COP. If we look at this from just a pure temperature standpoint, it is higher. So, the rules that Clay laid out in the beginning there play out here in real life, and we have a thermodynamic efficiency of around 65%. Now, that is a bit higher than what Clay had, and what I'd comment on that is this is an ammonia heat pump. Ammonia is probably one of the most efficient refrigerants available today, and it is a natural refrigerant. The main issue with ammonia is it's got a very serious, safety aspect to it. It cannot be released. That would be a very significant safety event for a facility. So that's why you don't really see it in commercial or residential applications, because it's pretty hard to manage from a safety standpoint. But you see it quite often in industrial applications because it is so efficient from a thermal standpoint.
I'd like to reiterate too that thermodynamic efficiency is not to be compared to a thermal efficiency. That's we're still well above 100% efficient. It's just a comparison of the actual efficiency compared to the ideal. Yeah,
that's probably something to reiterate and plug into. So when we talk efficiencies, we can mix numbers up pretty quickly. This isn't accounting for basically the free energy you get from the heat source that would shoot that efficiency up much higher than like a steam or a water heater, like Clay mentioned before. So you wouldn't really want to compare this efficiency to those. This is more comparing, the COP you're achieving, in actual terms versus the theoretical limit. When we talk about heat pumps, there are different types. All this really has to do is where is that heat coming from? Air source is very common because they're usually the easiest to implement. They don't require additional piping or pumping or anything like that. You're just taking the heat out of the air and pushing that heat into some other medium. Water source is, I think, growing in popularity. There is a bit more work with them because you do have to have a pumping and piping circuit for the water being circulated. but it is more efficient than air source. The last one, ground source, I would say is probably the least common, and it's the most capital intensive because you're digging wells and putting the piping and coils deep into the ground. They're very efficient as well, but like I said, from an implementation feasibility standpoint, it's much harder to get across the finish line with those. Clay hinted at this as well. A big driver of whether a heat pump will be viable or not is cost. And a phrase you'll hear often in these discussions is spark gap. And all that is the difference in cost of natural gas versus cost of electricity. So when you change from a steam or any kind of gas-fired system to a heat pump, what you're essentially doing is replacing that gas energy as a fuel to electricity. And so the cost is a big part of that. And if you have a really cheap electric rate and a really high gas rate, it's going to make the financials look much better. So if you look at this grid that we use for analysis often, it shows how that delta changes over time. At the far right is the cost of gas getting higher and higher, and on the left is the change in electricity. And you can see as electricity goes down the line, all the way down to 16 cents a kilowatt hour here, the financials get much worse. On the flip side, if the gas is pretty high, all the way up to 5 MMBTU, it starts to turn green and get to a point where we think the project's more viable and probably financials are much better. This will all change depending on the performance too. So that COP is really going to drive that electric performance, and if you can get that COP at a higher value, it's going to drive the financials of this as well, which is lines up with what Clay said earlier as well. So that this slide right here really shows how these two variables drive the financials of a project. If you have high gas and low electricity, it's going to look much better. And if that performance on the heat pump, the COP is really high, that's also going to be very helpful for the project. And I'll say over time, the COP of heat pumps keeps improving. If we were talking about this 20 years ago, people would have been kind of mystified. You were talking about heat pumps in an industrial setting because they really were meant for climates like Florida and places like that, and not really used anywhere else. Now heat pumps are really being designed for any climate, especially for the United States. They can be implemented pretty much anywhere in the country at this point, and those efficiencies keep improving as well. I touched on this a little earlier, but it's important to revisit. So, the refrigerant drives the circuit going through that compressor, going through that condenser and evaporator. What refrigerant you use is very important from a performance standpoint. Ammonia and CO2 are very popular natural refrigerants. Ammonia has that safety factor to it, like I said, but it is very efficient. The other thing to think about here is from a refrigerant standpoint, they have different temperatures that they can operate in. So not every refrigerant can work for every temperature. So you really need to understand what temperatures you need to operate at, and that will guide the refrigerant selection and system that you use for that. And there are regulation aspects to this as well. So refrigerants are getting phased out, and maybe a refrigerant you used for a system before may in the future not be used anymore from an environmental policy standpoint. So it's important to understand that and try to use refrigerants that are future proof, or just being understanding of what you're getting into when that refrigerant is selected. Now we're going to get into some practical examples. I'll lay out how a heat pump can be used to recover heat from a process and use that for a viable heat sink in an industrial setting. So I'm going to take the same diagram that Clay had here. So you've got your evaporator and your condenser and the compressor in the middle. But now we have, real life applications here with the sources and sinks. So on the source side, we have some water-cooled air compressors. They are currently rejecting this heat to an array of cooling towers. And instead of doing that, we would like to preheat the CIP makeup water that's currently being heated by steam. So let's see how that works. So on the left, you have the water-cooled air compressors. We're circulating that water that was going to the cooling tower through our evaporator on the heat pump, and then taking that heat and rejecting it to the incoming cold makeup water. We're calling this 80-degree water. So think, just your city makeup water, something like that, and preheating it before it goes into the hot water storage tank and the, steam set that would normally heat that water up. So as far as the value of that, we're now preheating that water to 150 degrees. You could say that maybe this water's final temperature needs to be 160 or something like that. And if you do the simple math, that comes out to 39 GPM. So as far as our options here, if the flow of makeup water is less than 39 GPM, then we would be able to heat it all up to 150 degrees. And then the final 10 degrees would have to be covered by the steam. Or if the flow is much higher than that, that temperature would come down. So instead of 150 degrees, maybe we just preheat to 120. But either way, we're able to throw all the heat that was being rejected through the cooling towers, consuming electricity that way. We're instead able to use that heat elsewhere in the facility and save gas and reduce carbon emissions. I did some basic math here. If you have a boiler efficiency of 75%, assume the CIP skid is running 50% of the time year round, and that's about 8,000 MMBTU per year, which at the $5 we've been talking about would be quite a bit of money saved. And on the carbon side, that's close to 1 million pounds of CO2 a year. So this would be a terrific heat recovery project if we found it. These are the kind of projects we look for when we go to a site. So I've got one more example. Back to the same diagram here. So on the heat source side, we have boiler stack exhaust. So if you're not too familiar with a boiler, I'll briefly describe the process. It takes in combustion air and mixes it with natural gas, fires it, and uses that heat to turn water into steam. Every boiler, though, after that combustion process is done, has an exhaust stack where that hot air is dissipated into the atmosphere. What we like to do is recover as much of that heat from the boiler stack as possible and use it elsewhere in the facility. And heat pumps are a great way to do that. So in this example, we take a economizer, take that energy from the boiler stack and transfer that heat to an incoming process. This is air, so we're not using water anymore. This is actually air source, and we're driving that heat into a makeup air for a food dryer. So if you're not too familiar with food and beverage, this is a very common piece of equipment where you have a conveyor belt. The food product will be rolling along and drying with some form of heat being applied to it slowly so that the food is dried and ready to be packaged and shipped out of the facility. Typically, this is going to be using a natural gas burner, and we'd like to offset that natural gas use by preheating the air. So doing a similar calculation, we work out that this could preheat a little over 12,000 CFM of air, and we could if the airflow needed for that dryer is close to that value, then we could preheat it all to 180, or if the flow is much higher than that, then we would just preheat it to a lower temperature, and then the gas burner in the dryer would do the remainder of the heating. Going through a similar calculation on the savings, if we assume that burner's 85% combustion efficiency running, pretty much all the time, if the plant's a 24/7 operation, that comes out to 13 MMBTU per year, which would be pretty significant savings, and over 1.5 million pounds of CO2 per year. So pretty good emissions reduction as well. So as far as when to get a heat pump involved in these kind of projects, it really comes down to your sources and sinks. Do you have a viable source of heat, and do you have a viable sink to put that heat in? Temperatures are also a big part of that. So, if you can't match up from a temperature standpoint, the heat pump's not going to work. The further those temperatures are apart, the bigger lift that heat pump has to work on, which is going to drive efficiency down, just like Clay overviewed before. So really all those factors have to be evaluated and understood before you know if a heat pump's going to be viable or not. The other big angle of this is cost. So we're trading natural gas for electricity. If electricity is overwhelmingly costly for the region we're talking about, then it's going to drive the financials of this down. For the same, or looking at it from a different angle, if natural gas is very cheap, it's also going to be hard to financially make this work for a heat pump. So that spark gap, the difference between the electricity costs and natural gas costs, is a big driver of the viability here. And that is my last slide.
All right, great. We're going to hang out here for a little bit and answer any other questions that come up. I know I have a question. I when we start talking about the heat sinks and heat sources, I start picturing all sorts of crazy solutions. And I was curious what you guys have seen as far as the most creative uses or capture of waste heat or heat sinks, heat
Yeah,
sources.
we have a beverage client where they're actually preheating the product before it goes into the main process heater that's all steam driven. So I think where the most innovation and opportunity is with heat pumps is actually taking auxiliary waste heat from utilities and things like that and integrating it with the process. So we're reducing the overall, gas-fired heating load in the process. We're seeing that a lot in the food and beverage industry right now.
You ever see
Yeah.
like a renewable source, like maybe a solar water heater system to create a heat source, and then tap into that maybe with some thermal storage or something? That's what I'm kind of. I haven't seen that, but I just
Well, I think the reason that's tough, I mean, Clay kind of hinted at this, the real magic about a heat pump is you're getting this free heat, free. So you're not having to generate that energy and pay the efficiency cost to do that. I think that's what solar struggles with, where the heat pump's actually just moving this heat from one place to the other, and you have to pay the little cost of the compressor, but that's really it. I think those other projects are certainly viable too, but they may not be as cost effective as a heat pump.
Okay. Yeah,
Yeah,
we've
one
looked at
thing
like
I'd add,
solar water heating for makeup water preheating and things like that. It doesn't seem to pay back fast enough, but there's a
Yeah.
lot of variables to the equation. But
Yeah.
yeah, the quantity of heat that they can generate is difficult there too. Just going back to your question before, Chase, one thing I'd say is I think Phil hit on this a couple times, and I think it's a really good point, is some of these applications work really nicely when it's doing preheating and you leave the existing heating systems in place. Phil talked about this with the CIP system. For those that are familiar with them, you might have something like a PIC heater, steam injection to heat hot water, and you can leave those in place and just preheat the water that is coming into those systems. Same thing with what Phil just mentioned with, preheating in that beverage application. I think that's really nice. The only other thing I'd say, Chase, is that you mentioned, other novel applications. Direct recompression of vapors. I got to go see a heat pump in Europe that was on an ethanol plant, and directly compressing ethanol vapors and then running that to a steam generator. And the same theory can be applied by applying mechanical vapor compression systems on the back end of any sort of evaporation system. So yeah, anyway.
compression cycles, but then you're taking, like in your simple example at the beginning, you're getting 400 kilowatts out for 100 kilowatts in. Now you're multiplying that input and you're reducing your COP, and you're just kind of taken away from the benefit.
Yeah, I would.
No, this
I'm
is great, guys. I let me we can hang around for more questions. I just want to do my kind of our closing in case anybody needs to drop off. We're coming up on the hour. But we'd like to thank everybody for mgt.com, which is right there. I'd like to thank our presenters as well. I think they did a great job, and we're lucky to have you guys. And we'll hang around for any questions that come up in the chat. We can hang around for a few minutes, but if anybody needs to drop off, you're welcome to do that. And thank you for attending. We'll also send out invitations for our but yeah, it's definitely interesting, and I'm hoping that for the sake of steam systems, it sounds like I guess Ashley said my mic went out. Hold on one second.
I
Yeah,
can
you're
hear
back
you
now.
now,
You're back
Chase.
now, Chase. Yeah.
Oh, okay. All right. Unless it went out for a second. Anyway, I'm just gonna say for the sake of steam systems, I hope they improve the technology for industrial steam generation or otherwise. And that's kind of part of our interest in it, other than just to learn about different things. But
I
I'm
do
sure
have a
everybody
question
enjoyed this
here,
topic.
Chase.
Oh, okay. I missed it. Let's see. Some comments. Do you have an example of an application where a heat pump needs to be used where a standard heat exchanger based on heat recovery system wouldn't work? I was kind of thinking that about the stack exhaust example, because
Yeah.
you can often take that and put it into the makeup water. So
Oh,
um
it's a fair statement. I would say that where heat pumps excel is where the temperature requirements are much higher. So you can get lucky in that your source temperature ends up being much higher than what you need from a sink standpoint, and then you just need a heat exchanger, right, to make that
mm,
work.
yeah, that's a good point.
The heat pump is what enables more heat recovery because it takes what we could call that low grade heat and makes it a higher temperature, higher grade heat, and you just have to use a little compressor energy to get there. So it's really temperature requirements that would drive the need for a heat pump or not.
Yeah,
And
that's
in
a
that
great point. So
vein,
you actually you're increasing the temperature potential with a heat pump, whereas you have to have a lower temperature application with a regular heat exchanger loop.
yeah, and in that vein, Chase, I'd add too that it might be worth investing more in that heat exchanger for the heat pump than it otherwise would be if it was just, a heat exchanger directly heating something, because these heat pumps are always going to be, limited on the amount that they can yield in terms of OpEx, right? And it might cost a little bit more for the heat exchanger itself to put in a heat exchanger that yields higher temperatures, coming out of it, or, a lower or a closer approach temperature to that heat source. But you're going to save on, years of heat pump operation. So it might be worth investing more in that heat exchanger just to get as close as possible to that heat source temperature so that you're maximizing the efficiency of the whole system.